Hello students. So today we are going to discuss about semiconductor islands, and they are basically self-treated by assembly by actual epitaxy. Now, when an atom or a group of atoms in terms of molecules, and they hit the substrate, there are three things that can happen. Firstly, it can absorb, on the substrate, and it will diffuse until liquid with other atoms to form islands. So when it is incoming atoms, this is substrate here, there may be some other atoms here, so they will get absorbed here, and then will be clustered with other atoms. They will liquid and cluster other atoms to form an island. This can happen. Otherwise, they can also attach to an existing island. Suppose there are already a group of atoms forming an island, so the incoming atom can come and get attached to that existing island, or the other thing it can simply dissolve from the surface and leave the island. So these three things can occur. Now, when an island is formed, it has to have a critical island size, below which it is unstable, and above which also it is unstable. And so it depends upon the rate of formation of the island, that there are some rates, like the rate of concentration of individual atoms, then pair of pair atoms, cluster size. So all these rates will play a part in formation of an island. So the basic equation governing the island formation is this one. It is RADS, which is the rate of adsorption, plus rate of detachment, plus 2RI, rate of breakage of bonds. These are the positive terms which help in island formation. The negative terms being the evaporation, rate of capture, and rate of formation of pair of atoms. So here you can see that there is a difference. Here it is a breakage of pair of atoms to form an island, and hence formation of pair of atoms to form an island. As you can see, RADS is the rate of adsorption, then rate of detachment, rate of breaking of atomic pairs. These aid in island formation, and those which are against island formation is the evaporation, capture of atoms by clusters, and formation of pair of atoms. Now there is something called superfluid clusters, where a cluster of 4 helium and 3 helium atoms can take place. And these superfluid clusters are formed by supersonic free jet expansion of helium gas. Now, whenever we say a cluster in this superfluid, we mean that there are not just any random number of atoms, but there are some fixed number of atoms. These are called the magic numbers, this being the cluster. So these are 7, 10, 14, 23, and 39, and this is for helium 4, and this is for helium 3. So the superfluidity in helium atom cluster for n is equal to 64 and 1 is equal to 128 atoms. There is double of that. So two atoms coming together having n64 atoms will form an 128 atom. This is superfluidity. We will call it superfluid because there is no viscosity involved, and it is a result of difference in both of the atomic particles having fermions and bosons. So as we know that fermions are particles which have only two particles can exist in each energy state, and spins are oppositely aligned, and bosons don't have any restriction. So as the temperature is lowered, moon and moon levels are occupied. So in energy levels. And we have a phenomenon called Bose-Einstein condensation, where all the Bose particle wavelengths are in wave, are in phase. So suppose there are fermions, so as we lower the temperature in case of a fermion, so you see that there are up and down spins, opposite spins at each energy level, not more than 2 per energy level. But in the case of bosons, lowering the temperature makes all the particles to sit in the lowest most energy level. This is what is called as the Bose-Einstein condensation, and this is what gives rise to superfluidity. Now, at the point where the superfluidity is achieved, that means at the point where there is no viscosity, viscosity is actually zero, that point is called lambda point. In the case of GW is 2.2 kelvins. Now, a difference between a superfluid and non-liquid is that a superfluid, while passing through a thin tube, for example, the normal fluid will pass slowly, and the things that will come into play are friction and pressure. But this is not in the case of superfluid. Fluid will flow smoothly without any viscosity. And there is a form called lambda point, and identification of a lambda point, that means the identification of superfluid state has been achieved, is when there is a discontinuity in the specific heat. By discontinuity in specific heat, we mean that to plot liquid helium with temperature. So there will be a certain point where suddenly liquid helium, the heat capacity, it's basically the heat capacity of the specific heat, you can say, this suddenly rises to this, and it goes down. That means heat capacity by specific heat is the temperature, is the amount of heat energy required to raise the temperature of 1 gram of material by 1 Kelvin. So after attaining a superfluid state, the amount of heat required to raise the temperature slows down, it actually drops down, and this is the lambda point, and this is a lambda point for liquid helium, and for the supercluster this is lambda point. Molecular clusters are individual atom molecules who form clusters. Like in the case of a water molecule, it is the hydrogen bond which is causing these molecules to cluster with each other. Now this hydrogen or this water molecule has got a broad Raman spectra due to this OH stretch between 3200 and 3600 centimeter inverse. So due to number of overlapping peaks from isolated water molecules, hydrogen bonding into clustering takes place, and the ambient is 80% of H2O. And as the temperature is increased, the cluster actually dissociates into individual H2O molecules.